absolute value of the set of parentheses function. So we're going to look at one more problem. So let's pick up. So this will be what language? Five. Okay. All right. So let's get to number 5. So for example, we have integral for and the absolute square root of x minus 1 x. So as I told you before, get to the end, to the next and the question will be just to find integral. So maybe we'll be looking at some problem where you have something like this. Now, there's 2 ways we can try to deal with absolute value. One is just to graph the function and see what kind of shape you have. If you get one of those, remember you should find integral in terms of areas. So you're looking at the picture and you're saying, okay, I see triangle. And use formula for the area going here to use the y side. Or if you have like semicircle, for example, something like this, you just put bracket and see. But there are some functions that you don't get anything with the straight line. So in that case, just by looking at the picture and trying to find any geometric formula, it will not work. So we have to see what we can do. So what we're going to do here, we're going to graph it. But we're graphing not absolute value, we're graphing the function itself. If you put y equals and then square root of x minus 1, so you will get this function. Not exactly clearly see the function, so let's kind of zoom in. But keep in mind, we like to see the interval from 0 to 4. Now, if I'm just going to zoom in, let's see what's going to happen. So I'll get 2, 5 will 10. So this is what I get. So it's still okay overall, but I really would like to see from 0 to 4. So probably I'll go back to original one, still go with zoom 2, but this time I'm going to move a little bit to the right. So let's see if something will happen here. Okay, so this is a little bit better. So I should graph. So what do we see here? We see the little portion of a graph is on the bottom. And we have to make it positive, that piece, right? Since it's absolute value, that's what we talked about last time. So you definitely have to split this integral into 2 integrals, not just one. And please.
We lost audio.
Lost audio?
Oh, it's really, really bad.
It's cutting in and out.
It's probably because of the weather. I don't know, guys. You're too far. It's cold.
Oh, it's working.
The
good.
words are being frozen, right, when they get to you. So, well, let's see. If control room can help me, I don't know if that's possible even.
It's working now.
All right, so let's see. What about now? Is it a little bit better?
Yeah.
Okay, good. So, again, by looking at the picture, we definitely see that we have to split it. So when we split this, we're going to have 2 integrals, one from 0 to 1. That's where we have intersection. And you have to be very careful here with the intersection. Right now it's nice, it's just 1, 0, right? But what if you don't have 1, 0? So you cannot guess here, it has to be specific. So in that case, you can solve the equation, take what? Square root of x minus 1 equals 0, right? Just solve the equation, get the intersection. Well, you can try to calculate as long as you can get nice number, then it's fine, okay? And you know how to find 0, right? You go to second, you go to trace, and it says 0, all right? So if you go to 2, and it says left bound, I have to go to the left from intersection. I hope you know how to do this, but this is what we have. Then it says right bound. We go to the right. And we talked about this. Our calculator is trying to use intermediate value theorem here. And then guess a little bit closer. So we'll get 1, 0. So that's good. And the second one will have from 1 to 4. So 2 integrals. So the first one, the one we're dealing from 0 to 1, you have to change the values from negative to positive, right? So that's what you do, just changing the sign and nothing else. So you have to put negative and then just square root of x minus 1. Don't forget dx. So you're multiplying your function by negative 1, and then we'll change the value. So now this area will be what? Positive, right? Because we put the negative sign, this area will be positive. So that's what we need. And the other one, since it's already on the top, above the x-axis, just keep it. So you have square root of x minus 1 dx. So we have to go through a little process here to get rid of that absolute value. There's no other way on the paper to do this. So now what I'm going to do, I'll make this a little bit easier for us. I will distribute this negative sign inside. I don't want to pull it outside. Okay, I'll put it inside. And my function now will be 1 minus square root of x dx. Do you understand? So you multiply by negative 1. Negative 1 becomes positive, so that's why I put it this way. And then we have the second piece. Well, we're just going to keep it for now. So now it's just a simple process. So nothing special we have to do right now. You just have to go and find antiderivative. Okay, so I'm going to get rid of the calculator. Hide it. So, all right. So going with this, what is antiderivative of 1?
X.
Will be just x, right? Now, what is antiderivative of square root of x? And you think about this as what? X to 1 over 2 power, right?
2/3 x to 3 over 2.
2/3 x to 3 over 2. Good. And then I'm going to close the parentheses to put the bracket and say from 0 to 1. Now, and you really have to practice finding integrals. Okay, we can get the concept. We understand we're looking for antiderivative, but you have to recognize, like here I'm going to do this, and there I'm going to do this. All of those things you need to see. Just knowing, like, okay, antiderivative, that doesn't help. The more you get integrals to practice, the better you will be. You get to the test, you will feel like, okay, I understand what's going on. So if you have a chance, pick up more problems. So that's this one. Moving to this one, it's still against root of x, right? So that will be what? 2/3 x to 3/2 minus x. But now I have to go from 1 to 4. So what we're going to do, we're going to substitute, right? And then just give you the answer. I don't care if you go through little steps knowing what that is. So here we'll get 1 minus 2/3, right? That's what you get when you substitute 1. And then minus, if you put 0, you'll get just 0, right? So I'll put minus 0. And then we're moving to this one. Well, now the bad news, you don't have 0 anymore, right? So you will have what? 2 over 3 times by 4, 2/3 minus 4. So that's the substitution of 4. And then minus, and we have to put parentheses, right? Because inside you have minus. So you get 2/3 minus 1. Okay? And from here, just use your calculator, okay? Whatever you want to do, but please get it right. And the answer will be 2. Okay? The answer is 2. Now, if you will go, for example, to check, like, did I do it right? So let's go to your calculator again, what happened last time I showed you, right? How to do it. So, the only thing I have to change the function, because I have to put what? With the absolute value, right? Because I want to see if it's right. So, absolute value, you can find this in math. Go to the right one, numeric, and ABS. So that will be absolute value. And then put the function. So square root of x, don't forget to close the parenthesis, minus 1. So careful again, don't change the function. And when we graph, I'm going to go zoom 6, okay, just to see what I have. So, doesn't look good, but I'm going to zoom again. Go a little bit to the right, somewhere over here. And then, so what happened, the piece that was on the bottom now is on the top, right? And what we'll repeat again, the process using calculator to find the integral. So, you go second, trace, which is calculate, and you go to number 7. And it's saying lower limit That's what? 0, right? So again, what we're doing right now, we're just putting this into calculus just to see what we have. So upper limit was 4. I'm going to hit enter. And the answer is not 2, right? You know what I'm saying? But who's right? Well, it's the same, right? We are right because we have exactly 2. This one, for some reason, I don't know why, but for some reason it was put like a decimal, 1.99. So you have to be careful because you may be like on the test, under all that stress, taking the test or doing homework assignment, you will look at your calculus and says, why is it not 2? Maybe I should put 1.99. Well, no, the answer is 2, okay? So we have to be careful. And I don't know what method calculator is using right now, like who was coding, putting all this stuff. I don't know what the method is using here.
My calculator got 2.
Hmm?
My calculator got 2.
Well, maybe the new version. What do you have, guys?
I have that same one.
Okay, so now which one are you using?
Oh, I have
No, I'm looking.
84.
Yeah, I got
So you have 84, so it still gives the same, right? Okay.
I bought a 4-year-old Casio thing.
Yeah, well, Casio always does more, okay? Even if I don't know if you've seen some Casio graphing calculators, they're amazing. TI is, they have good line of calculators, but Casio was always ahead of TI. And,
Why do we always use TI?
well, let's put it this way. And actually, what I'm going to tell you right now, this is a good question. Why are we using TI? It's actually, this is a true thing. When the first time TI came on the scene as a company, they had to market their product. And Casio was always on the market too. So somebody in the Department of Education in Washington, D.C. had a good friend. So that's basically what they had. There's no good reason why we're using TI, okay? It's just basically somebody in the education department decided to promote TI and everybody just picked up TI as the best product. That's not true. HP is also a good calculator. For example, if some of you will go into engineering, like here, say, I don't know about universities, but I think they do, you'll be working with HP calculator. We have a set of HP, so you will be getting HP calculator because if you go, for example, take engineering classes like statics, dynamics, or materials, then you have to deal with matrices with some different functions. Those calculators can do many things. TI is so limited, but blame those in Washington, D.C. Right? But it's true. Okay, so it's not a fairy tale. It's actually true. That's what happens, All right. So this one, let's do one more, and we're still working with the same section. Then I'm going to switch to the new one. Sum integrals. Let's put example. What is this? 6. Sum integrals look big and complicated, but after kind of thinking what can be done, you will see they're very simple. So for example, this one has some hyperbolic functions. Okay, so we don't need to calculate anymore, so this one has some hyperbolic functions. Okay, so it looks big, but remember, the first thing we have to do, we have to look at this and say, well, is there anything I can do to fit into the table? Well, the table doesn't have something enormous like this. The table has separately e to x, right? Separately sine, separately cosine. And when I say table, you know what I'm talking about, right? Table of derivatives or antiderivatives, right? The list of functions and all that. Well, there's nothing like this. But what you should catch, that e to the x, right on the top. This should give you a little clue that your hyperbolic functions also natural exponential functions, right? Can you substitute sine, hyperbolic sine with ease? Can you do it? Right. Same thing with cosine. So what you should do, you should change these two. So sine will be what? E to x, then what? What do you remember?
X plus E or minus X
Over 2, right? So that's our sine. Then cosine will be e to x plus e to negative x over 2. dx. Now, don't forget about dx. I'll take points off if you're going to throw it away. Also, this one we have. Now, it still looks big, but at least you can see, like, okay, what if I put everything over 2? So you have 2e to x over, and you have e to x minus e to negative x plus e to x plus e to negative x, and the whole thing is over 2. Then if you look, these two can be canceled, right? Can you see that? Okay. Then e to x plus e to x, what do you get? Alright, so you see how many things we can simplify. 2e to x over, we get 2e to x over 2 dx. Well, at first I would probably simplify these, kind of following the order. Here it doesn't make a difference. Now when I'm saying these, you see 2 division lines, right? And there's a main division line, that's the first one right here. Now for this example, it doesn't make any difference what you do first. You know, you can cancel e to x, okay? But I would follow kind of the process, and I work with these two first. Just to make sure that in the future we'll not make any mistakes with other problems. So first you do little divisions, then you do the main line. And then also now, if you look, if I copy this one more time, you have 2e to x over e to x dx, right? So what else you can cancel?
E to x.
E to x, right? So overall, that function, that big function that you saw from the very beginning, that with the hyperbolic sine and cosine, now is just 2. So now we will just get antiderivative, so 2 x from negative 10 to 10. Or you can also think about this as, remember, integral of a constant, right? Which is basically what? Rectangle. Area of rectangle. So that works too. So what do we have? We have 2 times 10 minus negative 10. Okay, careful with the substitution. And when we do this, we get 2 times 20, which is 40, and we're done. The only way to get good experience is to practice. Okay? Just, again, I say this so many times, but I'm just telling you from my experience. When I was learning about integrals, we had a separate book, just integrals. That book was probably like close to 400 pages, and it's just all integrals. And I did every single one. Just because I knew I had to get through. It's just practice, because everything can be changed, everything can modify, and every problem with practice will feel like, okay, I've seen it, I practice it. So there's nothing special about this. Again, like I said, you see we simplified here. With absolute value, we modify. No. No. A hyperbolic function is just basically to get acquainted that they exist, and we're using them in engineering, okay, overall, but nothing like I'm going to press so hard because you have to know them. You've seen them, you practice a little bit, and that's enough, okay? And if, for example, in any of your, I don't know, like say engineering classes or somewhere else you will go and somebody will say, well, we have to learn them, they will give you more. Because everybody knows that hyperbolic functions only were introduced once, like one section, nothing deep or specific, so that will be okay. Alright, so let's take a look at the one more, and then we'll move to the next section. I'll start the new one. So 7, we have integral from 0 to 1. We have 5x minus 5 2x power dx. Well, first thing, just think about going from left to right. Okay, don't try to create something big and something strange. Why I'm saying this, because like today we'll introduce another method of finding integrals. I shouldn't say another method, it's just if function will get more complicated. then we do this, okay? But overall, when you get to the test, it will be just the integral. It will not be specifically attached to any section. So you just find integrals. So you have to really fix this and differentiate, okay? Like in Calc 2, and I know guys, you have to take Calc 2, okay? But in Calc 2, you will learn, entire chapter 7 will be, again, all about integrals. And the biggest thing what you will be doing, it will be, I don't know, they will still continue to do it, but at least so far, up to this time, you will receive take-home exam. I know it's saying, like, it's too easy, I'll go home. No, it's 100 problems, 100 questions, all of them integrals. And if you look at 100 problems, like, what do I do, right? All the methods in one big bucket, and you really have to see the difference, all the different methods. So, I mean, it's all about practice. So here again, what I said. If you look at this, don't look at this from like, okay, it looks complicated. No, just go from left to right. Can you find antiderivative of 5x?
Yes. Yeah.
Right? So that will be what? 5x squared over 2. Okay, so done with this one. Now let's move to the right. So it says 5 to x. Can you find antiderivative of 5 to x?
Add to x over natural log of 5.
Right, so you should know this, okay? There's nothing special here, just straight from the table. 5 to x over natural log of 5. Now in section 5.4, I think I mentioned this, you will find table of antiderivative, but it's not the entire table, but majority functions are there. So you can just refer to this. Go to your book, ebook, get to section 5.4 and just look at that table. It's not a big one, but like I said, majority of functions are there. So this is your antiderivative. And you go from 0 to 1. So when we substitute 1, you get 5 over 2 minus 5 over natural log of 5 minus, and then when you substitute 0, right, when you substitute 0, what is this? This will be 0, that's right. But when you put 0 here, you get what?
1 over the natural log of 5.
1, all right, natural log of 5. So you have to be careful. Why I'm saying careful? Because for some reason we get this idea when we see 0 as our upper and lower limit, then we substitute it's always 0. It's not. It depends on the function, right? Then we substitute. So what do we have here? We have 5 over 2. I don't know if I have to write this, but I'm going to write this again. Plus, right? 1 over natural log of 5. So you get 5 over 2, then what?
Minus 4 log of 5.
Oh, look at the sign.
Minus 4
right? So,
log of 5.
all right, good. And we can stop. You don't have to find LCD here, okay? It's okay. But don't give me decimals. Again, we're not talking about decimals numbers here. Every answer is exact, okay? There's only one problem. We'll be on the exam. We'll get closer to the exam. We'll talk about this, where I will ask you specifically to give me a decimal. Okay, but nothing else. Everything has to be exact. And you know you can check this with the calculator, right? Converting this into decimal for your purpose, just checking, but not specifically. So, that's this. Now, like I said, I showed you just some examples.
Kennedy, maybe?
But I cannot show you every single problem that you will have. You go and practice, work with different functions, watch of those watches, need extra, get to your ebook, pick up odd numbers from 5.4, okay, and just go through those because they have answers. Okay? Any questions at this moment? Okay, so let's jump to the next section. So we still continue with integrals, okay? And we're moving to 5.5. And 5.5, we'll talk about substitution method. Or I'll put rule, okay? That's what book says, substitution rule. Well, the name itself says that I have to substitute, right? So why do we need this substitution? Well, what's happening, some integrals as a function, they're going to look big. And specifically when we have composition. Okay? When I say composition, what that means.
Functions and function.
Right, function inside of the function. So when we get to this and when we see composition, it's not going to be a straightforward method. You will not be able to find integral unless you reduce that integral to the look, to the form that you can actually see this in that table. So not everything will be so nice and smooth, but keep in mind not every problem from now on will require substitution. Okay? Substitution we need when we have composition. Okay? If we don't have composition, like with the previous example, you can just go and do it, or you can recognize antiderivative. You should not get involved with the substitution. So you have to be very careful. The other thing, what you can have, like you choose the substitution. You substitute, you work with that substitution, and you see like nothing's coming, like nothing works. Well, don't be afraid to admit that you chose the wrong substitution. Then go back and think about some other one. Okay? Now, sometimes when you can choose not 100% right substitution, when I say 100% right, I'm really talking about you chose the substitution, but this is not the best. So what can happen when you substitute, it looks like after substitution, you still should choose another substitution. So like twice substitution kind of thing, that means you just didn't pick the best one. So this is still a work, but not the best one, okay? But overall, this is the process. And some of them easy, some of them more complicated, some of them easy to see, but where the difficulty will come in with inverse functions. Again, inverse trig, okay, all those tangent, cotangent, sine, cosine. You really have to see those. Those problems, the most difficult ones. The rest, kind of okay. But with those, they're more complicated. And some of them really nicely hidden inside of integrals. And you will see this, okay, when you start working on your homework assignment. So let's just get to substitution rule and see how it works. So for example, well, this is just a general idea. Not everything will be like this. But as the idea, it's going to look like this. So first of all, I have indefinite integral, okay, to begin with. So for example, I have this. So as you see right away, I have a composition. But also something looks like this. Now this almost, if I will ignore this, okay, let me ignore the integral. This almost looks like what? If you think about derivative, I said almost, okay? Almost looks like what? What rule? Starts with C.
Composition.
We didn't have composition rule. If I take this integral away, this almost looks like what? What derivative? What math? Starts with C, then the second letter is H. Do I have to spell out everything?
I know what you're talking about. I just don't know.
CH, come on, people. Manika, I'm going to pick on you.
Chain rule.
Okay, well, sorry, Manika, you didn't have a chance to answer. Okay? It's a chain rule. So, it's not 100%, right? It's missing. F prime, right? But actually, substitution rule is the backwards rule for the chain rule, okay? So basically, we're working with the compositions. So what we're doing right now, we're kind of going backwards with the chain rule. It doesn't look like 100%, but you will see it actually works well. So when we're looking at this, let's say I have this integral in this form. So I recognize that I have a composition inside. Also, I have this little piece over here. Well, we'll talk about this g prime of x. When you start working with the problems, you'll recognize what you have. But basically, what we're saying, if I have something like in this form, it's not in the table. Okay, you cannot just go to the table of antiderivatives or integrals and say, oh, okay, I see it. Like 1 over 1 plus x squared is what? Inverse tangent, right? You know what I'm saying? It's not here. And it looks big and complicated. So what do you have to do with the substitution? And this is the only purpose why we have to use substitution. To change this expression over here to the form that will remind you something from the table right away. So our substitution normally we choose, okay, normally we choose this. Now let me show you how we do this. Now I know I'm not working with real function, okay, I'm showing you the process, then I'll jump and work with the real function. So normally we're choosing substitution. And the best probably to choose your substitution as your inner function, which is will be your substitution will be u equals g of x. Okay? Now, for example, if you take this and put it right now into the function, what do you get? You get function, right, of your substitution. Okay, so u will be over here. So it's not anymore g of x. It will be what? U. Do you understand? But the question is, what do we do with this? Because if I go with the substitution, all x's must disappear, right? Everything has to be in terms of what? In terms of u. Do you understand? This is how we do it. You're going to take the derivative of this. But instead of putting u prime, you'll put du over dx. Well, remember we talked about this notation, right? du over dx. And here you'll put g prime of x. I'm showing you the process with the function in general terms. Then we'll work with the real function. And what do you do next? You're going to solve this for du. Well, right now. So what is your du?
X times dx.
G prime of x times dx. Do you see this inside somewhere in your function? So what's happening right now, that you have integral, and here, instead of g prime of x dx, you're going to put what? Du. So now when you look at this integral that you have right now, it looks simpler, smaller, easier to work with. And normally this integral right here is easy to work. You go straight to the table and you know what that is. So what are you doing? You're downsizing. You're making that integral, this, smaller with something that you can work with. That's the goal of substitution. Nothing specific here. Again, when you will learn, again speaking to those who must take Calc 2, let's say, in Chapter 7, you will learn lots of different methods. And for example, you will still use substitution for some problems, but that will be, for example, trig substitution. So we'll use trigonometric functions as a substitution to make it smaller, easy to work with. But overall, the whole idea is to make it smaller and then usable to go to the table and work with this. So let's take a look at the first example. There's no big theory behind here, okay? So let's say we go to the first problem and we have this. Integral, and we have x cubed cosine of x to the fourth plus 2 dx. Now don't forget, this one is indefinite integral. So when you get to the end, you should put plus c, right? Alright, so if you look at this problem, you should recognize that you have composition, right? Can you see composition? It's not cosine of x, right? It's cosine of x to the fourth plus 2. Then you should think about this, okay, so my substitutions should be what? What do you think? What is your u? Just guess.
X to the fourth plus 2.
Right. Because you don't want to have cosine of this, right? You want to have cosine of something small, which is cosine of u, right? So putting equal sign, putting the vertical line, this is not absolute value, okay? It's just vertical line. And you say u equals x to the fourth plus 2. That's your substitution. Well, you cannot just substitute right now and say, well, I did. No, you didn't, because you still have lots of x's here. Everything has to be in terms of u, okay? So you have to take the derivative, and you get 4x cubed, okay? 4x cubed. And now, let's pay attention. You don't solve this for du, you solve this for dx. Because you have dx over here, you have to get rid of it. So you're going to substitute something instead of it. So what is dx when you solve? du over 4x to the third. That's right. Now that's all we need, so we're going to close the line. We'll put equal sign. We'll move and to the integral and continue. So we have integral x cubed, then we times by cosine of u, because that's your substitution. Then you know what dx is. What is dx? Du over, right? That's what we just did over here. This is your dx. You put instead of it. So 4x cubed. And overall, you hope right now that you still can cancel something, right? Because again, when you finish with canceling and your work, you should not have any x's. What do you see? This will be canceled, right? And the other thing is, can you pull out 1 over 4 outside of integral? Can you see 1 over 4? So you pull out 1 over 4 and you get integral of cosine of u du. And this is what I was talking about. Now look, integral of cosine of u du. Can you know, or do you know what that is?
It has just sine u.
So this will be just what? Sine, right? You understand that? This is straight from the table. That's the goal. To reduce it, make it smaller. So we get 1 over 4. We get sine of u. That's the antiderivative. So since you took the antiderivative, what do you put? Plus what? Plus c. But I hope you understand right now we didn't finish it. Because what do I have from the very beginning? What is my variable? X. So you have to go back to your substitution like a normal process with the substitutions. You go back and put your substitution into the function. So you get what? X to the 4th plus 2 and then plus c. And this will be the answer. Simple question. How do you know if you're right?
Take the derivative.
Take the derivative, that's right. So look, if you take the derivative, right, what do you get? 1 over 4, right? Then you get cosine of what? X to the 4th plus 2 and times by what? 4x cubed. And 4 and 4 will be cancelled and you get exactly the beginning. And this was 0, right? Okay, do you understand? Alright, so let's try another one. I know it's not enough, so we'll work at more examples. So we have integral of 2x plus 1 dx. Now, if I would have just like square root of x, well, it's a straightforward, right? Change it to x to 1 over 2 and then just go with antiderivative. But I have square root of 2x plus 1. Now, many students will change this 2x plus 1 to 1 over 2, and they try to go straight to antiderivative. You cannot, because it's a composition, you understand? Like I said, if it's square root of x, yes, do it. But if it's square root of x, 2x plus 1, you cannot just go straight to antiderivative. You have to work with the substitution. And it's easy to see what we have as a substitution. What is the substitution? Normally, I said, it's always what? Whatever sits where? Inside. So what is your substitution?
2x plus 1.
2x plus 1. Now never choose 2x, because then you have to do one more substitution. Okay? Your substitution is 2x plus 1, the whole thing. So u equals 2x plus 1. And then you get du over dx, and you get 2. And then what do I need from here? Dx, not du. I need dx. So what is dx?
Du over 2.
Du over 2. Alright, so that's all I need. So I have integral square root of u, right? That's what we have. If you substitute. And then you have du over 2. Well, you can move 1 over 2 outside. Also, you can change square root to 1 over 2 power, and that's what you have. So again, something that was a little bit larger as square root of 2x plus 1, we changed to square root of u, which is easy now to find antiderivative. So we get 1 over 2, I'm going to go slow here. And then what is your antiderivative?
2/3 u over 2.
And plus c. And you can see that you can reduce, right? These two. But also now you have to go back, right? So I don't know if I should write this like 1 over 3 u to 3/2 plus c, but I did it. Now we have to go back. So we have 1 over 3, then what? What was your substitution?
Plus 1.
2x plus 1 to what?
2 over 3.
Well, I think it's 3/2, right? And plus c. And this is the answer. Okay, do you understand? Okay, let's do one more. And actually, the one more will be exactly the same problem, except I'm going to use different substitution. Sometimes we can have different substitution. Okay, I will say this before I go to the next method or next substitution. This substitution right here that we had for number 2, it's the most natural one. Most students will choose this one. But there will be something special with another method, so I want to do it. So 3, we have integral square root of 2x plus 1 dx. It's the same problem, but I'm going to tell you what substitution I'm going to use. Okay, substitution actually will be the entire piece with the square root. So substitution is u equals square root of 2x plus 1. Well, like I said, this is not the most natural way of picking the substitution. Okay, normally we always pick something inside. But I want to show you something here. So the process is the same. Take the derivative. So this will be du over dx. And here you'll get what? 1 over, right? Then what?
With 2 dx plus 1.
So 2x plus 1 and times by what?
2.
2. Right?
Alright.
And we can cancel 2 and 2. Okay, so this is what we have. And then I still need my dx. And what is dx?
Du over square root 2x plus 1.
No, don't rush. That's the problem. Many students will do this. Actually do the right math.
Du times.
It will be du times by square root. You have to be very careful. You don't want, because most of the problems you actually will have division. And for some reason we decided it's always du over, du over. No. This time, if you look at this, it's a proportion, right? Dx times 1, dx, and this times this, right? So, what you have square root of 2x plus 1 du. You have a product this time. So please, again, don't assume anything. Actually do it. Well, that's all I need. So if I go with this, I get integral, and this one is my u, right? But then dx is square root of 2x plus 1 du. And then I look at this and say, well, in previous examples, I could cancel something, right? But there's nothing to cancel here. Well, what do you think you can do?
Can you,
And you have to be careful right now.
You
Look at the
substi-
problem.
can you substitute the u in there?
That's absolutely right. If you look over here, you have square root of 2x plus 1, and it's your what? It's to u again, understand it? So this time, you don't have to do anything special. You just call it u again. Because it's u, right, from the beginning. So what do you get here? You get integral u times u du. So this was nice and simple to fix, okay? But you should always be careful, because sometimes you get surprised like this, then you say, well, I did something wrong. You didn't do anything wrong. You just have to be careful and look again at your substitution and see what you have. So one more time, even if you got this one, you don't have a chance to cancel any x's over here, but it's exactly what you have as your substitution. So put u again into it. So you have integral u squared du. So that was easy fix, okay? And if you go with antiderivative, you get u cubed over 3, right? Plus c, don't forget that, and go back to your substitution. And we have square root of 2x plus 1 cubed over 3 and plus c. So here's my question. Are these two the same?
Yes.
Yeah. Okay. So why I really wanted you to see this third or second way of putting substitution, just because of this. Because as the result, when you start working, your goal is not to have x. The other thing what students sometimes assume, since you have du, okay, that this one over sub now is a constant. So you can take it and what? Pull it what? Outside. Remember we talked about this property? The answer is no, you cannot do it. Why? Because x is still the variable from the very beginning. You understand that? You're just manipulating this with the substitutions, but in reality, your u is function of what? Of x. Do you understand that? You're just changing the look. So never think that this is a constant. Okay? You cannot just take this outside of integral. Only if it's just 2 or 1 over 2. Do you understand that? So you cannot take it outside. Don't even think about this. And let me show you the last one right now for today. Just for today, because tomorrow we'll continue with substitution method. So the last one that I want to show you is this. And I know some of you still didn't get to your homework assignments, but remember, today is the due date, right? Just in case you forgot. But you should not to put this for the last moment, because you will forget lots of things. And then you're kind of trying to remember what was happening, and you have this visual picture, but you still cannot connect this. Now, I took this from the book, and I have no idea why they put x to the 5th after the square root. Well, overall, if I would do this, I would put it over here. Okay? But it doesn't make a difference, but still, it's kind of more natural to have x to the 5th in front. But that's what they have. Well, obvious again, if I think about this in simple terms, I cannot do it. There's no such thing as to distribute x to the 5th inside, which doesn't help anyway. Okay, you can do x to the 10th, 10th, right? And then put this distribute, but that's not the case here. So this one is the composition. So I can still use substitution, and what is my substitution? What do you think? Well, remember, you shouldn't question, like, what do I have here? Because normally substitution is what? Is your inner function, right? What is your inner function? 1 plus x squared, right? So 1 plus x squared. And then we'll go again, du over dx. So derivative of 1 is 0, right? And derivative of x squared is what? 2x. And I need dx. So here we have du over 2x. Now I want you to pay attention right now. See what's going to happen. So you get square root of u. Again, that was your substitution. Then you get x to the 5th. And then you get du over 2x. And we're just substituting. There's nothing else, okay? We're just substituting. Well, obvious. Again, obvious. 1 over 2 can go outside. Yes or no? You see 1 over 2? Right? 1 over 2. Usually 1 over 2 goes outside. Then inside you have square root of u, but then times by what? X to the 4th, right? And du. Alright, so it's kind of like what happened last time. You still have x, right? You still have x. And you have to do something to get rid of it. And we didn't do anything wrong. That was a good substitution. Now, if you kind of have this idea like we just said before, well, look at this and look at this. Well, that's not happening, right? You understand what I'm saying? Like direct move. But if you're paying attention, here's my question. Can you get x to the 4th from right here? Because you have to get rid of it. You must have u. X and u, they do not mix well. Can you get x to the 4th from here? If you what? Move what? 1 to the left, right? And then what? Square, right? You understand what I'm saying? You square. And that's how you get that x to the 4th. So what we have over here, I'm going to put this over here. You have u minus 1, which is equals to x squared. You see, that's another thing that you have to look at. And then, since we want to have x to the 4th, you have to square this. But again, don't make this kind of stupid mistake when you take this 2 and you do u squared minus 1. It's not u squared minus 1, okay? It's u minus 1 quantity squared. And then, you will substitute. So you have 1 over 2 integral square root of u, and this one is what? U minus 1 what? And du. And this is what we have. Now another thing the students may do here, they say, oh, I see u minus 1 like substitution again. No, it's easier if you just open parentheses. Do you understand? When you open parentheses, that's the easiest way to do it. There's no other substitution. Don't even think about substitution. So what do we have here? I'll change this square root to 1/2 power. Here, I'm going to FOIL, just in case you forgot, or use perfect square formula. This is u squared minus what? Plus 1, that's right. U minus 1 times by u minus 1, right?
I forgot you were on mute.
And then you distribute.
Okay,
And what we have here, if you distribute, you get u to 5 over 2. I'm going to go faster a tiny bit. Then you get 2u to 3/2 plus u to 1 over 2 du. And now what? Go with antiderivative, right? There's nothing else you can do with this. Just go straight with antiderivative. So we have this 1 over 2, and now we go with antiderivative. So plus 1 and divide it. So we have 2 over 7, u to 7 over 2. That's antiderivative of this one. I hope you don't have any questions here. Right, you add 1, you get 7/2. Minus, here we'll have 4 over 5, u to 5 over 2, and here we'll get 2 over 3, u to 3/2. And remember, this is antiderivative, so plus c. And we're going to distribute 1 over 2. Okay? And maybe just to save time, also what? To put substitution back. Do you understand that? Yes or no? I'm going to distribute 1 over 2, and then get rid of u, going back to my substitution. So, here I'll have 1 over 7, 1 plus x squared to 7/2, minus, remember we're doing 1 over 2, okay? Minus 2/5, 1 plus x squared to 5 over 2, plus, again, times by 1 over 2, so we'll have 1 over 3, 1 plus x squared to 3/2, and plus c. And that's the answer. It's big. It's big. Okay? So, tomorrow we'll finish, we'll still be working with this, okay? But I'm going to introduce also definite integrals. Okay? There's something special about definite integral, but it only starts, again, something special, only starts after when you find antiderivative. So you still have to find antiderivative. Okay? So, keep working. We're going to try to finish your homework assignment. Again, don't put it too far. Get as much as you can and start working on this one.
oh,